Hello, I'm Shengyi Qian, a third-year PhD student from the University of Michigan. Today I'm presenting our CVPR 2022 paper, Understanding 3D Object Articulation in Internet Videos. This is a joint work with Linyi, Chris Rockwell, Siyi Chen, and David Fouhey. First, let's imagine what we can do in this image. Besides detecting objects and reconstructing the 3D scene, we can also open the cabinet, drawer, or the door. It would be great if we can enable robots to have the same ability. One of the best ways for robots to learn this ability is watching humans doing this. Today we can find billions of internet videos on YouTube, and we can definitely find demonstration of object articulation. The problem is it's RGB only, without any 3D information. It's also noisy with a lot of human activities. From these videos, we'd like to build 3D reconstruction of object articulation like this. The girl is closing the microwave oven. In the recent few years, single image 3D has made a lot of progress, but the reconstruction remains static. There are also a few works which recovers articulation from RGBD, but most are on synthetic data. As our initial step to solve this problem, we collect a video dataset by searching Creative Commons videos on the internet. We end up with around 9,000 video clips, including articulating the dishwasher, laptop, door, and drawer. We annotate bounding box and articulation axes on keyframes. We have around 19,000 bounding boxes with 30,000 rotation axes and around 3,000 translation axes. Some axes are invisible. Okay, now we have an internet video dataset with 3D annotations. The next things we care about is how to reconstruct 3D articulation from these videos. We still don't have 3D annotations. Our key insight here is we don't need a 3D video dataset. What we need is a video dataset and another 3D dataset such as ScanNet. I'll talk about more details later. Given a video clip like this, we first split it into frames. For each frame, we detect articulating planes by extending plane RCNN. First, we have the bounding box. We can also have plane masks, parameters, and articulation axes. We first train the bounding box and articulation axes on internet videos since we have 3D annotations. We then freeze the network and train plane masks and parameters on ScanNet. Now we have per frame predictions. The next step is to track them and fit the articulation model. We use a ransack-like approach to select the best frame which explains the articulation process and use it as our final prediction results. Here are a few more results. This is opening a washing machine, opening a drawer, also opening a laptop. For qualitative benchmarks, we are interested in two questions. The first one is, can we just train on synthetic data, such as Sapien? We generate our own Sapien data and train our model on it. We find it has difficulty generalizing to internet videos, especially detecting the articulated objects, so we assisted with ground truth bounding box. The second question is, how does model-based approach work on internet videos? We choose D3D HOI as our baseline. We evaluate Sapien and D3D HOI on the task of articulation detection and use AP as the standard benchmark. The prediction is a true positive if the bounding box IOU is larger than 0.5, excess EA score is larger than 0.5, and normal angle smaller than 30 degrees. Here are our results. We end up with a box AP of 61.3, which is much higher than the D3D HOI. Our results are also much better than Sapien with ground truth bounding box on the box plus axis and box plus axis plus normal AP. Finally, we show generalization to Charades dataset without fine-tuning. It does a good job detecting articulations. For more information, please visit our project page. Thanks for watching.